So I think the other fun part of my job is I get to work with really smart people who are thinking about big ideas, who are teaching, they're doing their research, and there's a lot of those people right here at Bowling Green State University. And why it's so important that we have programs like this to have you come to Bowling Green State University to interact with some of these really smart people who are working on interesting projects is because we know that in the future you are going to be those people. So future provosts at Bowling Green and at other universities across the country get to work with really interesting, curious, engaged, bright individuals. And so we are so glad you're here at Bowling Green. And this program, which is the first in the state of Ohio and really one of the first outside of Virginia, we're really pleased that we have a professor from Virginia Tech who's taking his weekend to spend with us to begin to kick off this Kids Tech University. We are so happy you're here. If there's anything we can do at Bowling Green while you're here, you let us know. I'm going to be in and out because I'm kind of curious about some of these ideas too. And we love the fact that you're here on a really, really snowy day. So welcome to Bowling Green and have fun today.
Thank you, Dr. Rogers. Okay, now I get to introduce the star. Dr. Reinhard Laubenbacher is a professor of math at a place called Virginia Bioinformatics Institute and Virginia Tech. Now, Dr. Laubenbacher is a rather unusual kind of mathematician because rather unusual kind of people work at Virginia Bioinformatics. 10 years ago, he was recruited to this institute, sort of like a baseball team recruits an all-star pitcher so that they can win the pennant. And this institute was looking for mathematicians that had a special ability to talk to biologists, because lots of people recognized that there were really complex problems in biology that could be best addressed by someone who had a really fundamental understanding of mathematical tools that could be used. Dr. Laubenbacher was that kind of person. And for the past 10 years, he's worked with a number of biologists using his expertise to work on things like cancer and many other fields. But his interests extend beyond that to selling the idea of interesting younger people in why mathematics is a special discipline. And so about 3 years ago, he got this program started at Virginia Tech, Blacksburg, Virginia. And last year I had a chance to see it for the first time and hear a version of his talk. And to my mind, it was so special that I could probably say that if I was good enough and I was in your position, he might just be able to convince you that you really should be a mathematician. I think I was always interested in biology, but he could tell me that mathematics is just as interesting and just as important. So let's give a big hand for Dr. Laubenbacher, who's coming to talk to us today. Thank you.
Thank you very much.
I think you should be good. You got the light.
There we go. Thank you, Dr. Morris, for this wonderful introduction. That's a lot of pressure to live up to. It's great to be here despite the snow. Any of you have been on a university campus before? Wow, lots of them. Wow, lots of you have been. That's great. So you get a preview of when you graduate from high school what it is you can do. And this is another example of giving you such a preview. You'll see some of the sorts of things that people do at universities. So that's what we're here to do today. And so let me just, before we get started, let me just tell you a little bit more about myself, the sorts of things that Dr. Morris and other people don't probably know about me. This is a Google Earth image of the village in which I grew up and in which I was born. So this is in Germany. So Germany is across the Atlantic, and it's in Bavaria, so very close to Munich. And so this is what it looks like now. Now I was born in this house. Okay, I was born in this house. Now this is what it looks like now. I was born there 57 years ago. Right? It has grown a lot since. So you can imagine how small this was 57 years ago. Right? If you think, I mean, to me, you know, coming from a place like this, Bowling Green is a huge place. Right? It's a metropolis. So this is where I was born. I went to school. There was a schoolhouse. So here's the church. Here's the cemetery. This is where my parents are buried. And this is where the schoolhouse used to be. I went to a schoolhouse with 2 rooms, grades 1 to 4 in one room, and grades 5 to 8 in the other room. So we had 2 teachers.
I've actually been to Germany.
You have? Well, that's great. Who else has been to Germany? Oh, quite a few people. That's great. Okay. Anyway, so I grew up there, and at some point in my, once we got to high school, I was supposed to learn English. Okay, so I didn't speak any English. I just spoke German. Right? And people said I should learn how to speak English. So I said, well, why should I learn how to speak English? Right? Nobody in Bavaria speaks English. I can speak German everywhere. Right? So no need to speak English. Okay? So what happened, of course, is I ended up going to the university. I went to the university in Munich. I studied mathematics. And at some point, I ended up in the United States. Right? I wanted to just spend a year here, just to see what it's like. And really, I was sort of getting finished too quickly, and I would have to start working. And I said, well, I'm just going to spend an extra year going to another country. And what I really wanted to do is I wanted to go to Switzerland. Right? Anybody know anything about Switzerland? What about Switzerland do you know? The Matterhorn's there, big old mountain. Right? It's great skiing. I love to ski. Where I grew up, there are mountains very close. I did a lot of skiing. So I said, I'm going to go ski for a year, right? And do a little bit of studying. And unfortunately, somebody at the university said, well, you know, if you really want to learn mathematics along the way, you should go to the United States. So I came to the United States for 1 year. That was in 1977, long before any of you were born. And I'm still here. I never left. Right? I'm still here. So my life completely changed with that one decision. And you should keep that in mind as you decide what to do on small and large things. Those decisions can really change your life. And over the years, so I started out studying mathematics, and over the years, as Dr. Morris said, I ended up getting interested in applying the mathematical skills that I had to research in biology, and in particular in biomedicine, finding cures for cancer and other diseases. The mathematics is really, really important for that. Okay, so we'll have a lot of opportunity to ask questions. So if you have questions, you know, keep them in mind and make sure you ask these questions afterwards. There'll be plenty of time. So today's lecture is about patterns, and I'm going to tell you about patterns, and we'll explore some. So if I were to describe myself, what I do for a living, what's my job, I would say I'm a professional pattern hunter. I look for patterns. Okay, and that's what a lot of people do. That's what Dr. Morris does. He looks for patterns in different places than I do. And so that's what today is going to be about. We're going to look for patterns. Some patterns are obvious. They're very easy to spot. Other patterns are not so easy to see. And the first thing we're going to do is practice a bit. Right? We'll practice a bit to look at some patterns. And for starters, let's just look at some. Right? So what's this? What is that? Yeah, just shout it out. Pine cone. What sort of a pattern do you see? Yeah, spirals. Any other patterns anybody sees?
I see the at the top, grasses don't have any red dots on them.
Yeah, there are red dots here. There are no red dots here. Yeah, okay, very good. So here's a pine cone. What's the pattern here? Somebody, just say it. Clouds are sort of lined up in parallel. How does that happen? The wind makes these patterns. How does this pattern happen? How does this pattern happen? Do you know? Yes? I'm sorry? From a tree. It grows on a tree, but why does it grow this way? Well, you have to ask Dr. Morris about that. He'll be able to tell you. It's a matter of genetics. Right? That's in the genes of the tree. Now here's a pattern. What's that? It's a seashell. It's a seashell. There's a really cool pattern. We'll get back to the seashell, right? So what you see is this really nice regular spiral here and sort of these spiral type things here. And we'll get back to that, so keep it in mind. I'll show you this picture again before. So how does this picture happen? How does this pattern happen? Yes, somebody say it. Comes from a snail. It's made by a snail. Why does the snail make it that way? Well, Dr. Morris will tell you. It's genetics. Right? It's in the genetics of the snail to make a pattern like that. Right? It's another pattern that's made by a phenomenon that comes from physics. Right? You have a drop of water that falls into water and it ripples the surface and makes concentric circles. Right? Here's another one. Now this is, of course, not a natural pattern. It's a man-made pattern. This is made by a famous artist, M.C. Escher. And what do you see? How does it work? Right? It's a bunch of animals and people. Right? And they are arranged in such an incredible way that there's no empty space. So if you look at the space between these different, if you look at the white space, right, it's animals. If you look at the black space, it's animals. It's incredibly cool. Right? Actually, it turns out that he used a lot of mathematics to make these patterns the way they are. Here's a really cool pattern. So I'm very proud I took this picture myself. So a few months ago, I was in Spain in a place called Granada. And there is the Alhambra there. So the Alhambra is one of the 7 wonders of the world. It's an Islamic palace from the 14th century. And it is the most unbelievable place. It is full. Buildings, walls of buildings are full of patterns like this. So these are made from plaster. This is a plaster pattern. Right? And it's very intricate. There's a lot of mathematics has been used to make the symmetries in this pattern and create them this way. And finally, here's something called a Penrose tiling. Penrose is a mathematician and a physicist who invented a really cool way to make patterns. And we won't have time to talk about it, but if you just Google Penrose tiling, you will find very interesting ways to make tilings like this. Now, what I've shown you so far were static patterns. They didn't move. Right? Here's a pattern that moves. So what is it you're looking at? What do you think you're looking at? Yes? This is a macrophage that chases a bacterium. Right? So that happens in your bloodstream. Let me show you this again. Yeah, this little black thing, that's a bacterium. And this cell is chasing it and is eating it up once it catches it. Yeah, so this is a particular type of white blood cell. Right? So what's the pattern here? What is it? Why am I showing you this? Yes? Yeah, you might ask, how does this cell know where the bacterium heads to? How does it discover the pattern of the bacterium movement? And that's a good question. Anyways, and that one you saw before. So, how would you explain this pattern? How does that happen? Yes, somebody.
It's a moving pattern, and it just keeps going on and on and on again. And
Yeah, it's made by water that is pushed to shore, and then the surface of the ocean creates that particular water pattern. So it's something that you might explain with ideas from physics. So if you're going to learn physics in school, then that's the sort of thing that would help you. Okay, so these are a number of different patterns. Okay, and what I've shown you is natural patterns, right? Things that occur in nature mostly. I've shown you some artistic patterns. What are some other patterns that you observe in your life? Yes? Patterns on your fingers, certainly. Fingerprints, right? Fingerprints, what are some other patterns? Back there. You do the same thing over and over again, pretty much, right? You get up during the week, probably the same time to go to school, you brush your teeth, you eat some breakfast, you catch the bus at a certain time, right? These are all patterns. What's another example? Yes, back there. Yeah. Optical illusions. Oh, yeah, those are interesting. And one more. Snowflakes. Oh, very interesting patterns. Extremely interesting. Okay, very good. So what's a pattern then? Right? What's a pattern? Okay, so what I have up here is from Wikipedia, right? The online encyclopedia where you find lots of stuff. Okay, so let's just read what Wikipedia says, right? It gives you a definition of a pattern. A pattern is a type of theme or recurring events or objects, things that happen over and over, sometimes referred to as elements of a set of objects. These elements repeat in a predictable manner. So the most important word in here is predictable, right? You need to be able to predict things. Okay, now one of the two questions in my title is, why are there patterns everywhere that we look? Okay, can you answer that question? What would happen if there were no patterns in our lives? Chaos. Just pretty much, that sums it up, right? Right? Everything would be the same. Ah, how do you mean that? Ah, so that's, yeah, so what he's saying is everything would be the same. There are no patterns, so there's nothing to distinguish one thing from another thing. And that's exactly right? If there are no patterns, you don't know when the school bus is going to come. If there are no patterns in the seasons, then the tree won't know when it's supposed to grow buds and start growing leaves again, right? So whenever we have, or in your bodies, for example, right? If there are no patterns, then if you eat a piece of Twinkie, your body won't know what to do with it. Okay? And so the answer to the question why there are patterns everywhere is easy. Right? It's because without patterns, we wouldn't be here, and this world would not be here in the form in which it exists. So patterns are absolutely essential to what we do, and that's why we find them everywhere. Right? And the job of science in particular is to discover all the different patterns that we see and that are important to us. For example, patterns in how parts of your body change when you get a certain disease, right? When you get high blood pressure, or you get heart disease, or you get cancer, or you get an infection with a virus, right? We need to understand the patterns that happen in order to deal with this. So that's pretty much the answer. So the next question is, how do patterns come about? Right? How do they happen? And that's what pretty much the rest of what we're going to talk about will be about. Okay, so we're going to discover patterns. Some are obvious, some are not so obvious. So let's practice. Let's practice some patterns. Right? So one way you can practice patterns is to look for patterns in numbers. Right? Here we have 3 numbers, 2, 4, 6. What's the next number? Yeah, just say it. 8. There you go, 8. Next number is 10, right? I'm listing all the even numbers. So how about this? 2, 4, 8, 16. What's the next number? 32. I double from one to the next one. There you go, 32. What's the next number? What's the next number? What's the next number? How did I do that? Yeah, quiet folks. We got to hear what this gentleman has to say. Right, 5 plus 8 is 13. Exactly. So that's how it goes, right? Oops. Yeah, so that's how it goes. You keep adding things. So the next one would be 55. How many such numbers are there? Infinitely many. You can keep going, right? If you could count with very, very, very large numbers, you could go on for as long as you can. Now, these are very special numbers. They are called Fibonacci numbers. Okay? So they were invented by Leonardo Pisano Bigolo, who lived in the 12th century. And he wrote a book. He wrote a book about algebra. And these numbers are talked about in his book. So he's known as Leonardo Fibonacci. So they're Fibonacci numbers. Those numbers are very, very, very cool, and you should go and you should Google Fibonacci numbers. Let me just show you one feature of these Fibonacci numbers. Okay? So what I've done here is I've taken 2 numbers. So these 2 numbers you add up to get the next one. And what I've done is I've divided this one by the one that comes before it. Right? 2 divided by 1 is 2. Now then I take 3 and I divide it by 2, and I get 1.5. And I take 5 and divide it by 3, I get, and so you see, so I've just continued to do this. I've listed here the Fibonacci numbers up to 618, and I have divided like this. And so if I look at this number, at this point, right, the next one's going to be the same. What do you suspect happens if I keep going? Not so many this side. Somebody this side. Yes, sir. It'll give you the same. If I were to write it out to more and more decimals, right, it would become the same. Now this number here is a very important number. Has anybody seen this number before? Yeah, it's not so clear, right, how to answer this. Well, this number is called the golden ratio. Has anybody heard of the golden ratio? Or the divine proportion? Some have. You have. Where did you see that? In a book. What was the book about? It was all about math. That would make sense. All right, very good. It's the golden ratio. Now let me do something else. Right? Let me play the same game, but rather than starting with the numbers 1 and 2, let me start with the numbers 5 and 2. And I just do the same thing, right? So the next number is 7. The next one will be 9. The next one will be 16. Then we get 25. So on. Okay, we can keep playing this game. So we get a different sequence of numbers. And if you do the same thing I did before, you divide this number by this one, this number by this one, this by this one, and so on, you end up getting the same number. It's a completely different series of numbers, but their ratios are going to give you the same. And that's what I was saying. It's the golden ratio, called the divine proportion, golden mean, golden section. It shows up everywhere. So before I came, I looked. There was a research paper published in quantum physics. Right? So quantum physics, that looks at the physics of small subatomic particles, and they talk about the divine proportion as a particular number that shows up in physics experiments. And in particular, it's all over this place, all over this seashell. That number is all over that seashell. It's part of your homework, right? At the university, just like in school, you get homework. So part of your homework is to find out what this seashell has to do with the golden ratio. Any guesses? You have a guess? No, if you divide any number by anything, you end up with all kinds of things. So, yeah. Anyway, so that's your homework. Okay, very good. So now let's look at a different type of pattern that is related to something called SelfSimilarity. Okay, anybody heard that word before? You've heard about SelfSimilarity, okay? So let me talk a little bit about what SelfSimilarity might mean. Okay, so let's look at this. This looks sort of like a what? A tree of some sort, right? Yeah. And I mean, it's not a very good picture of a tree, I think, but it'll do. So it's a tree, right? So let's look at this branch of the tree. And let's suppose I just cut off this branch and I just look at this piece here. What does it look like? What's that? A giraffe. No, I don't think so. What does this piece look like? Well, it looks kind of like the whole thing, right? It looks kind of like the whole thing. And if I were to cut off this tree, right, if I were to just extend this a little bit, it would look like the whole tree, right? So parts of this tree are similar to itself. Okay, and that's what's called self-similarity. And we'll see a few examples, right? So here's a place where you see self-similarity, right? What is this? What is this? Way back there, what is it? Yeah, you. It's lungs, right? These are the airways in the lung, right? This is really, really cool. You know where you can see this? There's a very cool exhibit. It's called Bodies. I don't know if it's been here somewhere, but if you ever have a chance to see it, it's really great. What they did is they took a lung and through a very, very clever engineering, I guess, is they managed to preserve the airways and take away all the other tissues so you can see how this works, right? And if you look carefully and you take out, right, you take this part, let's say, and you cut off one of these branches and you pull it out, it looks just like the whole part of this lung. It's a very much a structure like this one that if you take apart, it looks very much like the whole thing. So this is a place where you see self-similarity. Another place is in fractals. So some of you might have heard about fractals. Who has heard about fractals? Okay, some people have heard about fractals. So one of the things I'm going to show you how to do is how to make fractals. Okay, there's a very cool website that allows you to make fractals. Okay, so here's a very important fractal. So it's a shape, if you like, a very important one. It's called the Mandelbrot set after the inventor of fractals, a mathematician named Mandelbrot. And so you see, I mean, you can already see from this picture that there's some self-similarity, right? If you look at this piece here, right, then it has this knob sticking out in the front, and the image is not very good quality, but if it was better quality, you would see that this piece here looks exactly like this piece. And the same up here. And then if you look at this piece that's sticking out here, it looks exactly like the whole thing. And if you go here and you blow this up, it looks exactly like the whole thing. Right? So let's see what this looks like. And you got to watch carefully. So we're going to blow this up now. And you end up with and you end up, as you zoom in, you end up with shapes that look just like the whole big thing, you see? And as you can keep going infinitely far. Right? So in small details, this looks just like the whole thing. That's the principle of self-similarity. Okay? And so what's your favorite animated movie? Yes. Beauty and the Beast. What others? Contagion. That's not an animated movie. An animated movie. Yes. Say that again. Tom and Jerry and the Wizard of Oz. Okay. So there's a range of animated movies. Now in almost every animated movie that comes out of Hollywood, a lot of the images are generated using fractals. Okay, so if you go and you work for Pixar, does anybody know what Pixar is? Pixar Studios, they make animated movies. You will have to know about fractals. Okay? You will have to know about fractals. Now, let me show you one way to make fractals. So this is a website which you can get to when you go to the Kids Tech University website. Right? You find the link, and what you see is this allows you to make fractals. And let me just show you some examples of things you can make. So here's a list of examples that this website shows you. Let me just go to some really cool ones. So here's a, oops. This is very slow. Okay, so here's an example of a fractal, right? Now you'd say, well, this is nothing special, right? It's a piece of what? It's a piece of fern. Okay, now how was this picture made? That's the trick. How is this picture made? So I'm gonna explain to you how this picture is made, right? And it's made by something you can do over here, right? So let's go back to the beginning. Let's see, how do I go back to the beginning here? Reset generator, there you go. You're exactly right. So what you see here is, if you look, let me just show this to you. Right, if you look over here, you see these white dots, right? And these white dots are hinges. These are hinges that hinge together these rods in between. And let me just show you that these are hinges, right? I can move them like this. Okay, let's just start small. Let's move this one, okay? So I have these 4 rods, they're hinged together. Okay, now I'm going to do the following. Right, and you can see that over here. Right, I'm now going to do the following. I'm going to take each one of these rods and I'm going to replace it by a smaller version of this whole thing here. Okay, let me just show you what that looks like. Right, so this rod here I replaced by this whole thing. This one I replaced by it. This one I replaced by it, and here. And just for fun, let me do it again.
Do it again.
Okay, and then let me do it again. And we may as well keep going, right? So you get something that looks like what? Like a bunch of cauliflower. No? Okay. So now let's do something different, right? Let's say instead of just having this grow straight up, it'll grow a little sideways. Okay? And I'm going to do it like lots and lots of times. Okay? I guess I would have to erase what was before. So I do it lots and lots of times. So what do you get? It's like a wave, you know. That's what it looks like. The wave sort of falls over to the left side. And which is sort of odd, right? Because this here falls over to the right side. So why does the wave fall over to the left side? Well, I don't think you know the answer. You're going to have to experiment with it, right? And so I can do other things, right? I can maybe move this here, and I erase this first, and I get some other picture, right? And so let's go back to this fern, right? So here's the fern, right? Now, how was that fern made? Well, it was made with this kind of arrangement, right? This looks pretty complicated. So you might not exactly think of that right away, how you might arrange these different lines, and you're going to have to read a bit about, you know, what these different colors mean. They mean different things. So it takes a bit of practice. It takes a bit of practice to learn how to do this. But once you know how to do it, you can make pretty cool pictures, right? And so the challenge is to understand how, as you make changes over here, how do these changes happen? What do these changes do over here? Okay. So this is a very cool website that you can go to. Okay. So this is enough enough about patterns that don't move. Right? We need to go to patterns that move. So let's get out of this. And so now oops. So now let's go to patterns that move, patterns that are dynamic. So let me show you one. Let me show you one. What do you think that is? It's birds. It's hundreds of thousands of birds. Okay? It's hundreds of thousands of birds. So how does that happen? How does that happen? Imagine yourself to be a bird, right? You're one of the birds flying around in there. How would you know where to fly? What do you do? What do you see? What do you know? Yes? You know when you're going to hit a tree. Well, maybe, because there are a bunch of birds around you. You don't see them, right? They fly high enough, maybe, so that they don't hit a tree. Let's just play this again, maybe. But so how does it happen? What if you're a bird? If you're a bird, what do you see? If you're a bird in one of these, yes?
I think like they make a pattern out of natural instinct, and they see a bunch of other birds flying around.
They see a bunch of other birds, right? And they don't see all of the birds. They just see, maybe 10, 20 birds that are really close by. And so what each bird sees is just a little neighborhood, right? What happens in the little neighborhood around it. But what you get is a pretty fancy big pattern, right? It's a bit similar when you think about it, right? All of you probably have seen an anthill, okay? Right? And so and it's a pretty large, sometimes a pretty complicated setup, right? It's a pretty big condominium complex that they've built there, right? And it's hundreds of thousands or millions of ants. So how do the ants know how to build that condominium complex? So let me, right, so the question is, right, we think that ants are not terribly smart. Okay, they don't have really big brains. And they sort of know, they maybe see a little bit what's around them. They can't really talk to other ants except in sort of non-verbal ways. But how does this all get organized, right? So how does a complex, large pattern come about by birds, for example, that only know what's going on around them? They don't have a good understanding of what sort of pattern should come out of this. And so that's a question I want to explore with you a little bit. And in terms of a computer game, although it's not really a game, it's called the game of life. Anybody heard of the game of life? You've heard of it. Some people have heard of the game of life. Okay? So what's the game of life? You can see here an instantiation of it. So these are a bunch of little squares on this whole thing, a bunch of little squares. Some are blue, some are black. There are some that have other colors, but let's just worry about the blue and the black ones. And if you start this up, if you run this game, these are going to sort of switch between blue and black according to particular rules. So let's look at the rules, right? So here I've drawn a simple version of this. So this game is played on a grid. It could be a pretty large grid with a bunch of squares. And these squares can be black or white. Now, why is it called the game of life? Because initially, John Conway, a mathematician who invented it, thought of these cells as being organisms. They could be people, they could be rabbits, they could be something. Organisms that live on this grid. And there are some rules about when organisms live or come alive or die, depending on what happens around them. So here are the rules. The rule is that it has to do with the neighbors of a cell. So let me say something about what the neighbors of a cell are. So let's take this cell here, this white cell here. what are the neighbors of this cell? It's any other cell that touches this one. Right? So this one is a neighbor, this one is a neighbor, this one is a neighbor. They're all neighbors. How many neighbors are there? 8. There are 8 neighbors. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now, if you have a cell with at most one live neighbor, right, like this one has only one live neighbor. Right? This cell has no live neighbors. Everybody around it is dead. Then this cell dies. So at the next step, this cell is going to die. A cell with 2 live neighbors stays alive. Okay? So where do we have a cell with 2 live neighbors? Do we have a cell with 2 live neighbors? How about this one? Right? This is a live neighbor and this is a live neighbor. So this has 2 live neighbors. It's going to stay the same. It's going to stay dead the next time. That's the rule. A cell with 3 live neighbors lives. So this cell here, for example, has 3 live neighbors. It's going to live at the next time, and a cell with 4 more live neighbors dies. It's too crowded, right? So the idea is if there are too few people around you, you're going to die. If there are too many people around you, you're also going to die. Right? So you just need the right amount of people. Okay? So let's see if we understand how these rules work. What's going to happen at the next time step? What's going to happen to this cell here? It's going to die. There's only one live neighbor. What's going to happen to this one? It's going to live. This one. This one. This one. Okay, well let's check. That's what's going to happen. Right? Because if you check, this cell here has 3 live neighbors. It's going to come alive. This one has 2 neighbors. It's going to stay alive. This one, just like the one above, has 3 neighbors. It's going to come alive. These 2 are going to die, and that's what you get. What do I get at the next step? This one's going to stay alive. These are going to die. These are going to come alive just like before. Right? That's what's going to happen. Okay, now, what's that? Okay. So that's an example. Now we understand the rules, right? These are the rules of the game of life. So now let me show you what sorts of things you can do.
This is Tim.
So what does this have to do with the birds?
Library 125 is a Mac lab?
Yes,
Yes.
somebody.
You know
Yes.
Yes.
Okay, good. Library 142
Louder.
is also available, and that's a PC lab. And there's a
Okay,
attendant
sorry, I can't hear you.
Okay.
and
What does it have to
works-
do with
she
the
works
birds?
with You. Her name is Josie, and she
Yes,
has
sir.
a key. She can open any of these.
Josie?
Josie?
Hug?
They all move in different directions, that's right. But how do they decide how to move? Right? The birds decide how to move by looking at the birds around them. That's all they see. A given cell in the game of life can only look at the cells around it, its neighbors, and decide what to do. Right? So that's the same principle. Right? You look at what happens in your little neighborhood, and if a whole bunch of people or cells or birds do the same thing, some very complicated and complex patterns happen. And that's what we're going to spend the afternoon doing. We're going to do things with the game of life on a computer. And that's the website here that we're going to go to. That's not where I wanted to go. Yeah, that's not where I wanted to go. But in any case, so at this point, you will learn more about what to do in the afternoon, and you'll be on a computer that gets you right to this website. So maybe we don't need to talk about what happens on the website right now, but that's what we're going to look at. We're going to make very, very cool patterns that move in the afternoon. Now let me tell you how all of this connects to the work I've been doing. This is a project I've been working on a few years ago. And it focused on something called the Epstein-Barr virus. Okay? So it's a particular type of virus that infects lots of people. In fact, 9 out of 10 people test positive for this virus. Okay, 9 out of 10 people. This is a virus in the family of herpes viruses. Right? Now, who has ever had a fever blister on your mouth? Well, you're maybe too young to have those, but that's a herpes virus, right? I get those a lot. I started to get them as a kid, and it stays with you. It never goes away. Once you're infected with this virus, you never get rid of it. Right? It is, in fact, the most important cause of the failure of organ transplants in children. Okay? And one way you get it is when you're in, usually you get it maybe in kindergarten when you play with other kids. Some kid is infected, you take a toy that they've dealt with, you put it in your mouth. You have it. What it does is in adults it can cause certain types of cancers. It causes lupus, it causes a number of other diseases. So it's an important virus, and what we wanted to understand is we wanted to understand how it is that this virus, okay, if you guys are not quiet, I need to scream louder, and then I can't talk in the afternoon. Thank you. And what we wanted to understand is where this virus is hiding from the immune system so that the immune system cannot get rid of it. And so what we did is we built a computer model of the part of your body that this virus hangs out in a lot of the time, and it is in the lymph tissue around your neck. So there are a bunch of tonsils, right? You know that you have 2 tonsils in here. Maybe some of you have had these tonsils removed. I've had my tonsils removed, but actually you have not just 2 of them, you have 6 of them that sort of form a ring around here. And that's where a lot of the action happens when you get infected. The virus replicates in that particular tissue. And so we built a computer model of that. And let me show you this computer model. All right, so here you see some of these tonsils, right? So here you see them. They go around. Right? And what you can see here in these charts, you see all the different types of cells you find in particular places. Right? So it does counts, and then you can zoom in to particular parts of these these tonsils and count virus particles and cells and other things. Right, so here's different types of cells. Here's the virus. So this is ultimately built for a doctor, right, to do experiments on a computer. So here you see a piece of a tonsil, right? Think back to the game of life. How does that remind you of the game of life? Okay, so what do you remember? What you saw? This little piece of tissue. There were these hexagons, little hexagons that were blinking, right? And the hexagons represent little pieces of tissue, and the blinking represents changes in the number of virus particles that sit on that particular region. So as the infection spreads, they will change. And the way we've built this computer simulation is essentially exactly the same way we built that the game of life is built. All these little hexagons, right? They have sort of rules attached to them, just like in the game of life. And the rules are different. They depend on different types of cells in the patches around them, but they're built exactly that way. So the game of life represents a way to build computer models of different things. So for example, we have a research group at my institute, some of my colleagues. So they are building they have built a computer model of all the 380 million people in the United States as they move around. And then you can simulate, you can infect some people with a particular disease, and you can see how this disease spreads in the population. And that way you can decide, for example, who do you want to vaccinate, which schools do you need to close to stop a disease from spreading. So somebody had seen contagion, right? So there's an example of how you can do that. So this technology, this game of life that we're going to explore in the afternoon, it's very, very important in terms of a technology to build computer models of all kinds of complicated things that we can't study in any other way. Okay, so I think I should wrap up and I should summarize. So what have we learned? Patterns are everywhere. And why? Otherwise, we have chaos. Exactly. Lack of patterns is chaos. Sometimes patterns are not so obvious, right? There are places where you need to look more carefully, right? I showed you the Fibonacci numbers. It was maybe not so obvious what the patterns are. I can show you much more complicated sequences of numbers where the pattern is really, really defined. And you need to do a lot of thinking to find them. What we've seen from the game of life is that simple patterns, simple rules can generate complex patterns. So what I should say about the game of life, there are a lot of researchers, scientists around the world who study the game of life. Right? So here's a question that nobody knows the answer to. Right? What you saw is you start out by making some cells live. Okay, and then you start this thing up. Can you predict what's going to happen when you start it up? Do you know what's going to happen? Right, you got these blinkers, right? We saw these three cells that are next to each other, and they sort of blink, but sort of stay static, right? Can you predict for which types of live and dead cells, which configurations does that happen? Those are all really important questions that a lot of people think about, and they're questions that you should also think about. So this afternoon, and when you go home, you can access these websites from home and do a lot of research, do a lot of experiments. Okay? So what's the upshot? The better we are at discovering hidden patterns, the better we understand the world. right? And it's important for us to understand the world, right? We want to know how we can cure diseases. We want to know how to predict earthquakes. We want to know how to predict tornadoes. Those are all matters of understanding the world around us, of finding patterns, whether it's weather patterns or patterns in the shifting tectonic plates. That is one of the key problems that science faces, is to understand hidden patterns. And you too can do this for a living, right? You can become a scientist. And here's a tiling that I showed you before, the Penrose tiling. Here's Penrose. He's standing here. This is at the Texas A&M University. He's standing in a building in which the floor is one of his tilings. They made a floor after his tilings. And I think the lesson that I want to have you go home with is that if you want to understand patterns, the right language for these patterns is mathematics. That's what you need to be good at. So studying mathematics in school and being good at mathematics in school puts you in a position to be a professional pattern hunter, whether you're looking for mathematical patterns, whether you're looking for patterns in biological systems, in cells, in animals, in humans. That is the key skill that you need to have. Okay, and with that I'll finish. So we have an opportunity for a question.
What is the function of the tonsil?
Ah, good question. What's the function of the tonsils? Well, so the lymph tissue we have around here, there are a lot of immune cells, among other things, that take place there. They replicate, and in part the tissue has a function of a filter. Right? It filters out stuff.
When you were looking around for that, what was it, that Game of Life thing, did you ever find a downloadable version of that?
There are downloadable versions of that.
Yay.
They're easy to find. There's a lot of stuff about all these things you can find on the web if you just use Google.
The one question that you asked about like the little white blood cell, I think I know how it like knows where it is.
Okay, tell us.
Antibodies.
Antibodies. Well, it's not quite right, but pretty close. Pretty close. What it does is it senses what's called a chemical gradient. So it senses certain molecules that the bacterium releases as it moves around, right? So it's sort of like it hunts the tracks.
It's like
right?
a
So the
smell.
bacterium leaves a track.
It's like a smell.
Yeah.
Can tonsils like die like if it's too infected or something?
Well, I don't know about tonsils dying, but when I had my tonsils removed, at that point they were in pretty bad shape.
Okay.
How do tonsils get in bad shape?
I can't hear you.
How do tonsils get in bad shape?
How do tonsils get in bad shape? Well, that's maybe a little too complicated for us to discuss here. So let's take that for some other time.
Could the flying of birds be related to genetics?
You mean the reason they form patterns of this sort?
Yes.
Would that be part of the genetics of these birds? Well, I would think so. Yeah. I mean, the fact that the birds do this behavior, they might still just orient themselves around using the birds around them, but forming formations like that, absolutely. I would think that's related to the genetics of the birds.
How do patterns and things like rocks form? I mean, they don't
and like they're not living things. They don't care if there's chaos or order.
I have a hard time understanding you.
How do patterns and things like rocks form? I mean, they're not living. They don't care if there's chaos or order.
How do
or
patterns in
anything like
rocks
that.
happen? Well, you need to look at how rocks happen, right? How do rocks come about? Maybe we'll leave that for some other time. But if you want an answer to your question, look up how rocks are formed.
You know, that will be an excellent question for the April issue of Kids Tech, because that's hosted by a geologist. And geologists really are the best people to tell us about how rocks form. And Dr. Yakubushi is a geologist and also a paleontologist, so she will be talking to you about fossils and a little bit about how rocks form.
Does anybody have a question about Fibonacci numbers?
What's your question?
Yeah. Let's take a question about Fibonacci numbers.
Why are they called Fibonacci numbers?
Well, because the person who first invented them, his name was Fibonacci.
Not about the Fibonacci numbers.
Somebody back there had a question about Fibonacci numbers. Let's have that.
Well, no, but why do they call fractals fractals?
Why do I think?
Why do they call fractals fractals?
Ah, I see. Well, so that's a bit complicated. It comes from the fact that there is such a thing called a fractal dimension, right? So you need to understand something about dimensions. If you take, for example, this thing here, then mathematicians would call this, it's one-dimensional. There's only one direction in which you can move, right? If you look at a plane, it's two-dimensional. You can move, right? If you think of the floor of this auditorium, you can move in this direction and you can move in this direction. So any move you make is a combination of moving this way and moving this way. Okay, and you can add a third dimension. Then you can move around in space. But there is such a thing as dimension 1.7 or dimension 1.5. There are things that have a dimension that's a fraction. Dimension, 5/3. If you've learned fractions in school, and that's where this comes from. The place to read about this is a very, very cool book by this gentleman Mandelbrot that I mentioned earlier. He has a book that's called The Fractal Geometry of Nature. And that's where you'll find out why these things are called fractals.
How do rocks get their patterns?
How do rats get their patterns? Rocks. Rocks. Well, we just had this question. You have to wait till April. The Kids Tech University faculty member who's going to talk to you in April will answer that question.
Does anything form in a Fibonacci numbers way?
Ah, that's a good question. So does anything form in the way of the Fibonacci numbers? So I would say yes. For example, that seashell that I showed you, right? The Fibonacci numbers are all over that. I told you to look for how that relates to the golden ratio, but the golden ratio is related to the Fibonacci numbers. So read up on the seashell and you find out all about how things grow and develop according to rules that come from Fibonacci numbers.
Would the carpet be considered a pattern?
A carpet?
No,
Well,
this particular carpet.
This particular carpet? I don't know. You tell me. What do you think?
Think what? That it would be. It's a pattern? Yeah.
Well, so what do you think?
Yes.
Does this have a pattern? Right, it must have a pattern because how is this carpet made? So this carpet is made by a machine, right? There's a machine that makes this carpet. So somebody has to tell the machine how to make the carpet. So somebody has to tell the machine what the pattern is to make the carpet. So there must be a pattern there.
Do you have a question?
How do you get the golden ratio?
Well, so one way I showed you, you take the Fibonacci numbers and you keep dividing successive ones that come next to each other. There are many other ways in which you can make that. So one story I just told to some people a little earlier is, for example, if you look in Germany, if you look at paper sizes in Germany, so the different, right, you go to the store and you can buy notepads. You can buy these notepads in different sizes. And in Germany, if you do that, then there's a really nice relationship between the different paper sizes. So if you take one paper size, sort of the equivalent of an 8.5 by 11, and you fold it in half along the long side, and you take half of it, you get the next smaller paper size. And the way that happens is you want to make a paper size so that if you take the long side, you take the length of the long side and you divide it by the length of the short side, you get exactly the golden ratio. So any size you make in this way, you get, when you fold it, you get again a piece of paper that has the same property, that the ratio of the long side over the short side is the golden ratio.
Why are mathematics called mathematics?
Well, that's a very good question. It goes back to ancient Greece, right? That's when the term mathematics was invented. But since we don't have a lot of time, what I suggest is you go to Wikipedia and you look up mathematics. It'll tell you.
Like, how does pattern begin in natural things, sort of like metals that you see sort of one solid color?
That's an extremely good question. You know, how do patterns in living things emerge? Right? And in fact, it's been a question that people have puzzled over probably for, I don't know, 50 years, 60 years, 70 years. Right? And there is a theory people have of how patterns in living things emerge. The theory was postulated by a mathematician, actually, Alan Turing, in the 1950s, who also is very well known because he essentially invented the computer, or close to it, key pieces of the technology that needs to go in a computer. He was doing this as he was breaking secret codes of the German Navy in World War II. But Alan Turing proposed a theory of how what's called morphogenesis happens, right? The formation of patterns in natural organisms. And it's very interesting. It's much too complicated to explain it here. In fact, the very first Kids Tech University lecture we had at Virginia Tech was by a very famous mathematician, Keith Devlin, who talked exactly about this for an hour.
For your job, is your job just in mathematics, or does it have science involved in it?
Oh, there's a lot of science in my job. So I work quite a bit with cancer researchers. I work quite a bit with experimental biologists. We need to understand a lot what we make computer models of. So we make computer models of cells, and so medical doctors and cancer researchers are involved in it. So I talk to lots and lots of different people. I talk to biologists, to biomedical researchers, to statisticians, to computer scientists, a lot of different people.
I'm going to cheat and ask you a question. What are the patterns that you see in cancer?
Yeah, so that's really, I think, at the heart of all of cancer research, right? What is a characteristic pattern that you see in cells as they become cancerous? And so people have discovered things that happen a lot of the time when a cell becomes cancerous, or happen most of the time, or even all of the time. But I would say at this point we don't really understand what the key patterns are in our bodies that make cancer develop. And I think a lot of research is still needed by a lot of smart people. Some of you, once you grow up, that question will still be unanswered.
How do patterns form?
Well, so I think we've talked about some ways in which they are formed. There's not one simple answer that covers all possible patterns. If you explore the fractal patterns and the game of life patterns, you'll get a good idea, at least in some cases.
What are some main things you'll know if you want to have a career in mathematics?
What are some things you need to know? So one thing to realize is that the math you learn in school now, right, is really the foundation that you need to understand more complicated math, right? So what we talked about for the last 45 minutes, I would guess probably most of you don't think that that's mathematics, right? I talked about mathematics all the time here, the whole last 45 minutes, right? But what have we talked about? We've talked about discovering patterns in all kinds of different settings, and that's what a mathematician does, right? So what you need to do is you need to learn, I think more than anything, you need to learn how to solve problems, right? If you train to be a mathematician, you train your brain to solve problems, right? So by the time you're done, your brain looks like Arnold Schwarzenegger's body, right? Some of you might not know who Arnold Schwarzenegger is, but he's a big muscular guy.
How are mathematics and science related?
Mm-hmm. Yeah, that's an excellent question. Well, it so happens that mathematics can be used to describe a lot of things in nature. So there's a very famous saying by Galileo Galilei, right? So some of you might have heard of Galileo, right? Who was Galileo? Somebody, yes. He was an astronomer, right? He was a 15th century astronomer, 16th century astronomer. And Galileo said, the book of nature is written in the language of mathematics, right? So even back then, and that turns out to be more and more the case. The more we look, we can describe natural phenomena, whether it's in astronomy, whether it's in physics, in chemistry, and in biology, we can describe them through mathematics and mathematical equations.
How did you get so interested in patterns?
How did I get interested in patterns? Well, so let me tell you why I decided to study mathematics. Okay, so actually when I decided to study mathematics, I was really not interested in science and engineering and any of these things. The reason I studied mathematics is because I viewed mathematics as art, abstract art. So I wanted to be an artist. That's exactly why I got interested in it. And so what do artists do? Artists make patterns, right, of different kinds. Obvious patterns, not so obvious patterns. You know, whether you look at a novel, there are patterns in a novel, there are patterns in paintings, there's patterns in music. So that was my initial interest in mathematics and in patterns.
How does pattern science and mathematics all relate into, how do they all relate to each other?
How do they all relate to each other? So I would say, and that in part gets back to a question we just had earlier, why is mathematics so useful to describe things in nature? See, I think, right, so some of you, probably most of you understand how a computer works, right? So you have the hardware, that's sort of the box and the transistors and various other things, that's the hardware, and then there's the software, right? So if you have a Windows computer, then you have Then you have the Windows operating system that's part of the software. That's how the computer thinks. Okay? And I think that the way we think, the way our brains are wired, is they are wired basically mathematically. Right? We are wired to think logically. And that's why everything we can understand, we can only understand through the lens of mathematics. That's why.
Could all patterns have begun from one thing, like the Big Bang?
Oh, I see. Could all patterns have a common origin? Right? So you have the Big Bang and then everything sort of just unfolds from there. Well, so that's a big question. So a lot of people have worried about this. A lot of people have worried about, or not worried, but have thought about whether everything in the universe is determined, right? From the point of view of the Big Bang starts, is there anything random in the universe? Some people think no, some people think yes. And depending on where you come down on this argument, the answer to your question is yes or no.
How was science created?
Yeah, people created it. People created it because they wanted to understand the world. That's how you get started as a scientist.
Why is the golden ratio called the golden ratio?
Well, that's a long question. I'll defer to Wikipedia. Go and look at Wikipedia.
Are patterns all the same shape?
No, there's lots of different patterns. There are patterns that move, there are patterns that don't move, there are patterns in colors, patterns in shape, lots of different ones.
How do patterns form by themselves?
How do patterns form by themselves? Well, I don't know that patterns form. Yes, I don't know that there's a good question that would be. Right? One can talk about specific cases of specific patterns. So you might ask, for example, sorry about that. Okay. Yeah, so the question is, I guess whether the way people talk about this is whether patterns emerge or whether patterns are created. Right? And so I'll let you think about that. Give me, think about an example of a pattern that you think just happens by itself.
How long have patterns been on Earth?
Forever.
Why do different patterns move and some don't? Why do some patterns move?
Well, because there are patterns in things that move and patterns in things that don't move. So you find them everywhere.
Why do patterns form?
Why do they form? I don't know.
How is the pattern up there formed on the screen?
So that's a complicated question. You need to learn some mathematics to understand that. It's built using some mathematics that you don't know yet, and that you haven't learned in school yet.
Are there patterns in everything?
Yes. Yes, there are. Okay.
And thinking back to that one about the patterns and the Big Bang, I then thought of, how I remembered the entropy, I think I'm saying that right? Mm-hmm. Process of how everything gets more complex and more chaotic with that.
So entropy makes things less complex, right? So patterns sort of disappear and dissolve, and you get something that looks more chaotic.
So we have time for 2 more questions.
Anybody have a question about what it takes to be a mathematician, or rather better, how to become a mathematician?
Okay. We'll answer that question.
how long do you have to go to school for, and like what degrees do you have to get?
Right. Yeah, so what you will need to do, so in my case, for example, right, I went to high school until about 18. Then I went to the university and I got a bachelor's degree, an undergraduate degree, then I got a master's degree, and then I got a PhD. And I was done, I think, when I was maybe 29. And then I became a professor at a university. So it takes a while, but you know, there's lots of stuff for you to learn.
What does mathematics have to do with studying cancer?
Right. Well, there are many ways in which mathematics is related to studying cancer. So the way we use it is the computer models we build of cancer cells. They rely on mathematics to get the motion right. Right. So if you let cells evolve, they are based on mathematical equations.